Welcome to Discover ASAP, the video interview series where we highlight the top findings and tools connected to the ASAP network. Today, I'm talking with Neil Dundon from Team Strick about the SoCal Kinesia Incentivization for Parkinson's Disease, or SKIP, dataset. Neil, thank you so much for joining me today. To start off, can you briefly tell me about your ASAP project and the impact you hope to have on the Parkinson's disease space?
Hi, Dana. Thanks so much for having me. So our project is about identifying novel brain circuits that might help movement in PD patients. This is Team Strick's goal. It's a collaboration involving animal and human studies, both here at UCSB, at USC, and at the University of Pittsburgh. So we take it from both across a cellular circuit and a systems neuroscience approach to try and identify novel movement circuits. And the particular circuit that we're interested in is inspired by tracer studies in non-human primates that suggest that there could be an alternative pathway to facilitate movement that is not impacted by PD, that involves portions of the basal ganglia and projections from amygdala up to the motor cortex, this open loop circuit. And we think that this circuit might facilitate movement in situations that are surprising or emotionally evocative, given the role of the amygdala. And this is consistent with clinical observations in some people with Parkinson's can have a condition called paradoxical kinesia, where at moments of surprising or emotionally evocative situations, movement is restored. So situations such as catching a child out of a falling chair, but the exact situations are not very well understood. We've also got cases where it involves catching a ball or riding a bicycle. So there's lots to explore here, and this is one particular circuit that we're keen to try and identify.
Great. So as I mentioned, we're here to talk about this data set that you have been collecting as a part of your work with Team Strick. So I'd love for you to talk to us a little bit about how this SKIP data set, and really I guess it's data sets, how this relates to your ASAP project and what you guys are trying to accomplish there.
Yeah, absolutely. So as I mentioned, the paradoxical kinesia is typically facilitated in surprising or emotionally evocative situations that require some kind of fast movement response. So the whole goal of this data set is to try and see in humans what circuits in the brain facilitate fast motor responses in such situations. So it's kind of taking together effective neuroscience and motor neuroscience. We're trying to meet in the middle. So we're not just interested in brain regions that respond to emotionally evocative situations. We're not just interested in the the areas that control motor movement, but specifically the areas of the brain that speed up this response in emotionally effective situations. So
go ahead. Sorry.
So we're very much at the human end of this. So as I mentioned, we're a collaboration across cellular, circuit, and systems neuroscience. So our partners in Pittsburgh are looking at this also in rodent models, looking at it in non-human primates, but in terms of then translating those findings into clinically useful information. Our particular goal here at UCSB is verifying circuits in humans.
Great. That's really interesting. So I'm going to ask you now to dig a little bit deeper into the specific data sets that are available within SKIP, and ask to give us a brief overview. You've already mentioned that this data set is human data, but can you talk a little bit more about the tasks and the kinds of measures that you guys are that are included in this data set?
Yeah, absolutely. So the SKIP dataset contains 4, as you say, data sets. So 3 of those data sets are a combination of behavior and fMRI. So we have human participants in an MRI performing movements in different situations that we present to them. And the 4th data set then is a high resolution resting state data set. So starting kind of with that latter data set first, this data set is more about verifying the connectivity patterns in the brain, the circuit that we think is facilitating movement in paradoxical kinesia. Well, can we actually see evidence that the nodes of this circuit actually communicate with each other, just purely like uncovering the architecture, so to speak. Then when it comes to the actual behavioral data sets, these were collected at UCSB in a 3 Tesla MRI scanner, and they were quite challenging. So we have a combination of different ways to bring about emotionally evocative situations involving things like electric shock, involving things like financial incentivization. And we also want to record movement and the kinematics that are elicited by these situations. So we have people in a scanner, moving a joystick and doing, quite complex movements for an MRI task. And so I can go into now more detail about the specific experiments that we're doing. So
yeah, that would be great.
So the first of these behavioral experiments is called the incentivized vigor task. And this is to see if, as people move the joystick to hit targets, if every once in a while a target will give them a high level of reward, does that facilitate an increase in speed? And or conversely, if every once in a while, if they fail to hit the target, will we penalize them and take money from them? So it gives us that way of looking at both sides of an incentive coin. We can see both positive incentives and negative incentives. Mm. And this is all while we're recording the MRI data that allows us to do correlational analyses to see what regions of the brain are facilitating that increase in speed in those different incentive situations. So that's the incentivized vigor task. We then have an active escape task, which is purely about the incentive of escaping harm. Here, they have a small patch attached to them as they're in the MRI scanner that will deliver an electric shock if they don't move fast enough. So they see this countdown timer on the screen, which lets them know when the electric shock is coming. But if they can move fast enough, they can actively escape that electric shock. So again, it's about seeing, can we create a situation that brings about an emotional incentive to move quickly? And then we can do analyses to see what in the brain controls that. And then the final of the behavioral tasks is called an approach avoidance task. And this is all about dialing in on the congruency of certain kind of almost reflexive movements that we have for certain type of stimuli. So if you think of like a very positive stimulus, like a puppy, you would instinctively approach that. Or if you think of a negative stimulus, like say a picture of someone holding up a gun, you would naturally avoid and move away from it. So again, when there's this congruence between the emotional valence of the image and the typical movement associated with that, does that also potentially facilitate faster movements, and what are the brain regions that control that?
Great. I think that's a great overview. This is, I think, a massive undertaking, it seems, collecting all of this data. I guess, despite the massive undertaking, I think, of collecting these 3 task-based data sets in addition to the resting state data, I'm curious if you and your team have plans to expand into other assays that might, be relevant to this sort of intersection of emotional salience and motor movement.
We are, and I should probably have clarified that all of those behavioral data sets are young, healthy controls. They're all, in terms of the sample size, it's about 70 participants have done each of the 3 experiments. So we can actually make comparative analysis within the same person being incentivized in different ways. And in terms of then expanding our assays, we're certainly looking at it. We're piloting a study at the moment here at UCSB that's exploring fast escaping objects. So the idea that you have to reach toward an object that might move away quite quickly at any moment, which some studies have shown can speed up the vigor of movement in people with PD. So again, it's not quite so emotionally salient, but certainly given that this area is quite poorly understood, it's just another idea of some kind of a situation that might encourage people to increase their movement speeds. And we're definitely going to be looking into that too.
Sure, I think that makes sense. So you've just mentioned that you have recorded these tasks and the fMRI data in healthy controls. Can you talk about your plans to expand the data set into the PD population?
Absolutely, and we're really excited about this. We've already had 7 PD patients come into us here at UCSB and have successfully completed the IV task and the approach avoidance task. And moving forward, the plan is to bring in our partners at USC and start increasing recruitment for PD patients in the Los Angeles area. We're hoping to get closer to 50 and include that clinical data in the SCIP dataset as and when that becomes available.
Great, that is super exciting, and I think leads really nicely into my next question, which is I'd love to hear you speculate about what your hope is for this SCIP data set and how it might be reused for future discovery about motor movement and emotional salience writ large, or about Parkinson's disease more specifically.
Yeah, so absolutely. As I mentioned earlier, like we're dialing in on one specific circuit, and it's inspired by tracer evidence in non-human primates and other evidence. But there are obviously like countless possibilities for motor circuits in the brain, and a lot of those motor circuits might similarly respond to the sort of incentives that we're creating in these experiments for human participants. So the first area that I'm very excited about contributing to with this open source data set is if in future either rodent models or non-human primate models might identify alternative circuits involving sites that are not affected by Parkinson's disease. And the data set is there, it's ready to go. Like you can now do your analysis on human data, performing emotionally guided movements. And so that would be the first area that I'd be really excited about. The second area would be obviously analyses themselves are getting increasingly more advanced, including like network neuroscience approaches, and not just dialing in on nodes of a circuit, but rather how the entire brain is configuring itself in different circumstances of incentive. So that's another area where we would be super excited to see the open access data being used. And then not quite so related to PD, but aligned to all of this is how people move and the contributions that we can make to things like AI robotics that are trying to identify if it's a neurobiologically guided synthetic form of movement, understanding how humans move in different situations, what we prioritize, what we completely discard when things become highly emotionally relevant, I think is a hugely expanding area of research. And things like full self-driving cars, making decisions in emotionally relevant situations, or indeed just kind of knowing more about how the human motor system and human motor decision making is affected by life or death situations, for example, in terms of then developing co-pilot technologies that could take over and guide us through these moments. So lots of areas there could in turn then come back and assist PD. And these are all avenues of exploration that we're really excited about.
Great. Yeah, I agree. I think that's super exciting. And I really like that you brought up the AI, because I think, one thing that we really believe at ASAP is that you can't anticipate the future use in many ways, or the future discovery that could come out of your data set. And so I think, sharing the data set in this very intentional way is great, because it does open the door for not just others in the Parkinson's space, but in potentially quite different spaces like AI and self-driving cars and so on, to really utilize this data for future innovation and discovery.
Yeah, absolutely. And part of that innovation too will be bringing this back to like a very relevant area for Parkinson's disease is, of course, brain stimulation and the deep brain stimulation techniques to facilitate movement. it's about identifying where to target, but also how to stimulate these areas, different frequencies and different pulses and stuff like that. So if, as we move forward, we can start identifying in emotionally evocative situations, not just what regions of the brain are active and controlling movement, but perhaps through what types of kind of signals are being sent, that we can then perhaps fine tune and help refine these stimulation technologies, could be another huge area as well.
Yeah, definitely. Very exciting. So I always end my interviews by offering you the opportunity to add any additional things that you want to add about your data set, or about how people should access your data, any extras that you want that I didn't ask you that you'd like to include.
Yep. So anybody interested in the data sets that I spoke about can log on to SoCalKinesia.org. And there we have a description of the data sets, links to where they're hosted online. They're free to be downloaded immediately. I'm available for any kind of help that anyone might need. I'm on Blue Sky at Neil M. Dundon, and absolutely thrilled to talk to anybody who wants to use our data, or just talk about ideas moving forward.
Great. Thank you so much, Neil.
Thank you.